Here's time. All right. I think it's time for me to get started. Yeah, I'll begin. I will begin with a word of prayer. Dear Father, we thank you for this day. We thank you for the break completed, and I just pray that you be with us today. Help us to glorify you what we do, and just understand a little more about collisions, Lord. You know my prayer, Lord Jesus. Amen. All right, so collisions, yes. This is physics, right? So it's calculus. Okay, I mean we could do calculus. I don't mind.
I would prefer not. I already had that this morning at 8:15.
So we talk about collisions. Collision typically has, well, I mean, it doesn't have to have just two things, but I most of the time consider two things coming together, colliding, and then they go their separate ways, right? And in a collision, momentum is conserved, all right? Now, energy may or may not be conserved. And so we have two kinds of collisions, right? Inelastic, kinetic energy not conserved. Elastic, kinetic energy before equal to kinetic energy after, all right? So those are the sort of two kinds of collisions we can think about, kinetic, elastic and inelastic. Let me start us out with an example here. So, example one, I have a car with mass 1,000 kilograms. It collides with a truck of unknown mass. All right, we'll call that M2. All right, and after it collides, the composite mass travels at 50 degrees with respect to the initial path of the car. Supposing the two paths were perpendicular and the car initially had 20 meters per second, whereas the truck initially had 40 meters per second, determine the mass of the truck from the given data. Also find the speed, Vf, of the car and the truck after they're stuck together. So let me draw a picture here. So here's the intersection we're thinking about. I've got a car. Here it has V1 initial is 20 meters per second. All right, over here we've got a truck. All right, it's going in a perpendicular direction with V2 initial of 40 meters per second. All right, this one has mass M2, this one has mass M1, right? I'm saying M1 is the 1,000 kilograms. They collide, right? And I tell you that they go off at 50 degrees from the initial direction of the car. So they collide here, and then they do something like this, all right? So up here, we have M1 and M2 stuck together with some final velocity, Vf, right? And I'm giving you, oh man, this marker smells like death, 50 degrees. Not in a good way either. Barbecue, think about it. So, all right, so make sure I've got all my things defined here properly. So this is the situation. The question then is, what's M2 given that this happened, all right? So we also assume that mass is neither created nor destroyed, right? So like the total mass of the car truck stuck together after it's collided, right? Imagine they're covered with Velcro, they stick, you know, whatever. But the net mass here is M1 plus M2, right? So the way we solve this problem is we assume that momentum is conserved, right? Because in the process of the collision, there's not enough time for an external force to change, right, the momentum of before and after. So we can think of the car and the truck together as a system, which is essentially closed to the moment right before to right after the collision, all right? So we can conserve momentum in such a collision. Now, of course, if time went on and the truck car system skidded to a stop, well, then the momentum would go to zero, right? Because an external force, namely the force to friction, would be reducing the net momentum of the system, right? But that's not the problem we have here. Okay, so here we go. The momentum for the first thing initially, plus the momentum for the second mass initially, is equal to the final momentum, right? And so here we have m1 v1I plus m2 v2I is equal to m1 plus m2 times vf as a vector, right? But given the coordinate system that I set up, right, we can figure out what is vf. So vf as a vector is the magnitude times what? Times cosine 50, sine 50. You guys agree? By trigonometry here, like the horizontal part, cosine 50, the vertical part, sine 50, the magnitude, vf, yeah. So what we have then is we've got m1 times 20 meters per second, comma 0, plus m2, which we don't know, times what, 0, 40 meters per second, is equal to m1 plus m2 times vf, right, times the vector cosine 50 degrees, sine 50 degrees. Now, let's see here. What was I given? Yeah, so I'm supposed to try to find the mystery mass and the final velocity here. Do I have enough information? What do you guys think? I think we can rewrite this as, let's see here, so m1 was what, 1,000? So I got 20,000 kilogram meters per second for my x component here, right? And then 40 meters per second times the unknown mass m2, right? And that's equal to what? Apparently it's equal to, m1 plus m2 vf times the cosine of 50, and then likewise m1 plus m2 vf times the sine of 50. I do know what m1 is here, right? I'm just writing it that way because that's easier than writing 1,000 in those spots, okay? Can we do this? Like, can we solve? So in order for this vector in order for this equation to hold, we have to have both the x and the y matching, right? So I have 20,000 is equal to this business right here, right? And I also have that 40 meters per second times m2 is equal to that. So let's write those down. We have m1 plus m2 vf times the sine of 50 is equal to m2 times 40 meters per second, right? And bless you. And we also have m1 plus m2 vf times the cosine of 50 is equal to 20,000 kilogram meters per second. So what kind? These are my two equations, right? My two unknowns are what? M1 and VF. What should I do to solve this algebra problem?
Solve for M2 and then put it in the other
I heard to solve for M1 and put it in the second 2 equation. Not a bad idea. Can somebody tell me how to be lazier though? I just heard that already. I want something lazier. How about this? How about I take this equation and divide by that equation? So this over that. What happens? These be canceling. I get tangent of 50 is equal to m2 times 40 meters per second divided by 20,000 kilogram meters per second. What you guys were telling me about solving a substitute, that was a responsible, reasonable answer. But I wanted an answer that would be more offensive to like algebra teachers, so this is what I did. So this gives me that m2 is equal to apparently 20,000 kilogram meters per second divided by 40 meters per second times the tangent of 50 degrees. So m2 apparently is equal to what? $595.9 kilograms. Wait a minute, what? 595.9 kilograms, yeah. So apparently we're not talking about like a full-size truck here. We're talking about like one of those little Chinese deals. Have you seen any of these around? Like they're more than, there's like they're like a smart car, but a pickup truck, right? That kind of deal. Although it does seem like the smart cars aren't correctly labeled. Just saying. So does that make sense? Anyway, did you guys understand the algebra that I just did? To reiterate, conserve momentum, work out the algebra. Now what's VF then? You could use either one, right? Either one we could use. I'll use the second one. Well, I think I like the blue one's better, right? VF equals to what? VF equals to m2 times 40 meters per second divided by m1 plus m2, which was what? m1 plus, that's 1595.9 kilograms. That's my m1 plus m2. And sine of 50, yeah? But I probably should trade out my m2 for what? m2 was 595.9 kilograms. So if I crunch the numbers here, what do I get? I get 19.50 meters per second for my VF. Now we can check our answers here. What would be a good way to check the answer? What should the x momentum be after the fact? It should still be what? It should still be 20,000 kilogram meters per second, right? So we can check, is m1 plus m2 times VF times cosine 50 actually equal to 20,000? Let's try it out. Hopefully I have a calculator. All right. So let's see here. M1 plus M2, 1595.9 times my alleged VF of 19.5 times cosine of 50. Make sure I'm in degree mode. I am in degree mode. I get 20,003.6. So yeah, up to round off error, I've got just about 20,000 plugging these numbers into this formula up here. All right, so what's underlined in red, it works out to just about 20,000. So yeah, I think we're right. Any questions? Is this what do you guys think? Is this going to be a kinetic or is this going to be elastic or inelastic collision? What do you think? Elastic? Inelastic. Okay, I heard what I shouldn't have. So yeah, I think inelastic is definitely the case here. How do we figure that? How do we show it's inelastic? Right, so what's the kinetic energy before here? Try to fit it in here somewhere. So kinetic energy initially is 1/2 times 1,000 kilograms times 20 meters per second squared plus 1/2 times 595.9 kilograms times 40 meters per second squared, right? That would be my initial kinetic energy. And that works out to what? Did I actually calculate it? I did calculate it. Woo! 676.7 joules. I bet that's a kilojoule. Yeah, kilojoule. Which sounds much cooler, really. So there you go. We started out with 676.7 kilojoules. How about at the end, what was KEF? 1/2 M1 plus M2, which was 1595.9 kilograms, times my final velocity, which was 19.5 meters per second. You got to square that. That gets me kinetic energy of the collided car mass system. And that actually works out to 303.4 kilojoules, right? So as you can see, comparing these, it's inelastic. Energy is lost in the collision, right? Where does the energy go? Well, the energy goes in like the deformation of the car and the truck as they stick together, sound, whatever else, other things. It has to go somewhere, but it's no longer kinetic energy. Momentum conservation is not up for grabs, all right? Like momentum conservation is inescapable. Kinetic energy conservation is a privilege, may or may not actually happen. So there's a couple of special, well, okay, so here's something I'm going to copy from my notes pretty much straight because in previous years I have tried to derive this on the fly, and it's bad. You could go search the archives. You'll find me spinning my wheels for a long time on this one. This one's tricky, very tricky. So here's the theorem. And here it is. If MA and MB undergo a one-dimensional, watch this, elastic collision, then VA initial minus VB initial is equal to parentheses minus VA final minus VB final. In other words, if you have a one-dimensional collision which is elastic, the relative velocity between the colliding masses is minus what it started with at the end, all right? So like a simplest example of this theorem would be something like you know, here's a very simple example. You have MA sitting here, you have MB over here like that, and it's got initial velocity v naught, and then after you have MB sitting here like this, and you have MA with velocity v naught. Sorry, it's already bothering me. Well, for the purpose of this example, which we'll call example 2, I'm going to assume that MA and MB are equal, all right? Then you can see that with that assumption here, what's the initial momentum? It's just MB V naught, right? What's the final momentum? MA V naught, right? But if MA is equal to MB, the momentums are equal, so momentum's conserved, right? Kinetic energy being conserved is also going to be true, right? The initial kinetic energy of the B mass is 1/2 mv naught squared. The final kinetic energy is all in the A mass, right? 1/2 ma v naught squared. But you see the difference. Here we have, VAI minus VBI is equal to minus V naught. Over here, I have VAF minus VBF equals to V naught minus 0, which is V naught, right? So as you can see, that's equal to minus VAI minus VBI. So the relative velocity, as you can see, is minus what it started with. This is not an accident. This is like generically true for a one-dimensional collision which is elastic. All right? Any questions? I'm going to work out the theorem in a second here. So if it's an elastic collision, so here's the sneaky thing, is like, and it seems like it shouldn't be that bad, but if you just try to work this out in general, assuming that both of the masses are moving at the start, the algebra gets really annoying. And so the algebra is much easier to follow if we work out the algebra in a particular frame of reference. And so what we're going to do is we're going to look at the frame of reference where the B mass is initially at rest. I need to erase the blue part because I got to write up here, if that's okay, guys. So, I did move the camera, right? Yeah. Okay, so here's the deal. I'm gonna let A be moving with velocity V naught to start with. And it turns out, without loss of generality, I'm going to put mass B here, and this is initially at rest. And you might say, well, that seems like you're making kind of a special assumption. And that's true, but the thing is, we can switch to another frame of reference. If initially if the B mass is moving, we can move to the frame of reference in which is co-moving with the B mass, such that the velocity of the B mass is 0 with respect to that other frame of reference. And at the end of it, if you just do a constant velocity shift of one frame to another, all of the velocities just get shifted by the same amount. And if you look at what we're trying to prove, if both of these get shifted by the same amount, then the same result still holds. If we can prove this in one frame of reference, it's true in all other frames of reference, which differ just by a constant velocity shift. So that's kind of a sneaky step, but it's important to make the algebra not so horrible here. So this situation, afterwards, we have MA and MB, all right, but this time with the VAF and VBF, all right? All right, so then what? I am assuming an elastic collision. So what's the deal? We have 1/2 ma v naught squared is equal to 1/2 ma VAF squared plus 1/2 mb VBF squared. So this is assuming that kinetic energy is conserved, right? And then what else do we know? It's a collision, right? So momentum is conserved. What's momentum conservation look like here? I disagree. MAV naught is equal to what? It's equal to MA VAF plus MB VBF. And we're working with one-dimensional conventions where the sign, plus or minus, of the velocity indicates either rightward or leftward, right? So, great. So this is kinetic energy conservation, and this is momentum conservation. So then what? Well, then what we'll do is we're going to put, just to make the algebra easier to follow, we'll let V equals to VA. Oh man, I've already violated my notation. We'll let V equal to V naught, is what I did here. And we'll let VA be equal to VAF, and VB equal to VBF. All right, so that saves us a little bit of writing. With that, we then find that V squared is equal to VA squared plus MB divided by MA VB squared. Where's that coming from? So what I'm doing is I'm taking this equation right here, right? And I'm converting it to that. How do I do that? I multiply by 2 and I divide by the A mass, right? So I'm assuming the masses are non-zero, right? So I have that. Then the next move here is to get from conservation of momentum that VB is equal to MA times V minus VA divided by MB. That's from conservation of momentum. In other words, we could solve for the fraction, which is to say that the ratio of the masses, MA over MB, is equal to VB divided by V minus VA. All right, so that's from momentum conservation. There I have used this character right here and an algebra step to get to there. All right. So then what do we do? Then I will plug in this fraction formula I just found into the kinetic energy formula. So I'll put that up here. That gives us V squared is equal to VA squared plus, all right, MB over MA. So that's VB over V minus VA. That's my fraction here, and then VB squared. All right.
Fraction, like it's opposite, like MB over MA versus
I think the fraction's okay. If this equation's right, because I'm just dividing that to the other side.
I'm saying when you put it into the equation above it.
Oh, you don't believe you believe my algebra is wrong?
Well, you have the
It is,
V over MA
it is
versus
possible.
MB.
So V minus, yeah, I think it's okay. Because I just subtract this to the other side, and then I divide by MB.
But you substituted MA over MB into MB over MA.
Oh, you're saying that step is bogus. No, that's possible. That's very possible. Oh, yeah, thank you. Let's see here. So I think you're saying I need to flip the script here, right?
Yeah.
So V minus VA, thank you, divided by VB, yeah. All right, so what happens here is oh, huh. Okay. Well, I have done the algebra a different way in the notes, which is weirding me out, but there's about 1,000 different ways to do this. Anyway, so VA squared plus parentheses V minus VA times VB is equal to V squared, right? So we have this. Then what can I do with that? Well, I say subtracting VA squared from both sides. So I get V squared minus VA squared is equal to V minus VA times VB, all right? But notice that this right here gives me V minus VA times V plus VA. All right? So how can that equation be true? What are your choices here? Logically speaking, either we could have like we could have V equals to VA, right? Or what else could we have? We could also have V plus VA equals to VB, right? So either V is equal to VA, which in cases we have 0 equals 0, it works, right? Or V is not equal to VA, in which case we can divide by the V minus VA factor, and it leaves us with V plus VA is equal to VB, like so. What does it mean if V is equal to VA? If V is equal to VA, in other words, this in my original notation, this says that V naught is equal to VA. In other words, it says that VA initial is equal to the VA final, right? That's a fancy way of saying the collision didn't really happen, right? I mean, that basically that just means that mass A comes in and just keeps going, right? That's not really the thing we're looking for. That's not a collision, right? So apparently this is the solution that's physically interesting. And what's it say? That says that V is equal to, VB minus VA. But notice that this is VA initial minus VB initial is equal to minus VA final minus VB final, which is what we were trying to show. All right. So there you go. But this is just a one-dimensional derivation. If you try to prove this in 3 dimensions, like a lot of the derivation goes through just the same, and eventually you basically find your way to like I've thought a lot about this. So like in 3D, you end up with the equation. If you go through the analogous calculation in 3 dimensions, you get V dot V is equal to like VA dot VA plus. Oh man, I'm trying to get to the point here. This is still a middle step. In 3 dimensions, you get to, trying to get straight to the end of it, but very similar calculations, you get the VA dot V minus VA is equal to VB minus V dot product with V minus VA. And the thing is, that's as far as you can go for like the higher dimension. Like if you try to do this same derivation in higher dimensions, it falls apart. The reason being, all the same calculations basically go through, but the wrinkle is, at the end of it, you get to here. Instead of, like this equation here is the analogous one, right? Like I have here, well, I guess the roles of A and B maybe have flipped around, but same idea. So basically this is like that, and this is like that, but the difference is these are scalars. And we could divide by a scalar, essentially, if the one is non-zero. On the other hand, here, I can't divide by a vector. It's very possible for these 2 equations to be equal, and yet for, V minus VA to be non-zero. It could be that V minus VA is perpendicular to these, And yet still we get equality, yet no, I mean, you can't draw the same conclusions in 3 dimensions. This is a one-dimensional result, okay? We don't have this result for elastic collisions in more dimensions, unfortunately. So the larger thing I'm trying to communicate to you guys is that elastic collisions are rare. Inelastic collisions are plentiful, at least for physics problems. Elastic is harder to come by. Let's see here. But notice that one of the takeaways you should get from this theorem here is that if you have a one-dimensional example and you're asked, is it elastic or is it inelastic, it's very, very easy to check using this theorem, right? For example, 3, if I have a one-dimensional problem, and before I have MA with 10 meters per second, and I have MB with, I don't know, 20 meters per second, and then after I have, MA with 5 meters per second this way, and I have MB with, I don't know, whatever you want, 20 meters per second that way, let's say, then I can check out VAI minus VBI. So VAI would be 10, and VBI would be minus 20. So my initial would be 30 meters per second for here. On the other hand, VAF minus VBF was apparently 5 meters per second minus 20 meters per second, also known as minus 15 meters per second, right? And that is clearly not equal to minus VAI minus VBI, right? So thus, collision not elastic. That's one of the primary uses of the theorem I'm just sharing with you, is it gives us a very quick way to see if a collision's elastic or not in one dimension. Now in more dimensions, I can't just do this, unfortunately. All right. I think I didn't move the camera. But the camera didn't miss much. Let's see here. So any questions here before I go on? No? All right. Example 4. Suppose we have M2 equals to 10 kilograms, and I have here M1 equal to, I don't know, let's say 3 kilograms. And M1 has initial velocity of 10 meters per second, all right? And let's suppose that these collide and they stick together, all right? Actually, let's not suppose they stick together. We already done that. Let's try something different. Let us suppose that after the collision, let's suppose that M1 slows down, and it only has a speed of V1F, let's say. V1F equals to, let's say, 1 meter per second. And then we've got M2, right? And we'd like to know what VF equals for that, right? So can we find this? Can we find the velocity of the second mass, given that this is the collision? And after we do that, we can ask the question, was it an elastic collision? All right? Do we understand the question? I'm telling you, and I probably should tell you that this is at rest. right? I need to say that. Otherwise, the problem's not well defined, right? We need to know what's the initial condition of both masses. And so there you go. Now, so the question then again is what's the final velocity for the second mass? And then follow-up question, was this an elastic collision? So conserve momentum, right? So the initial momentum is equal to the final momentum. So here I've got, 3 kilograms times 10 meters per second is equal to 1 kilogram, wait a minute, no, still 3 kilograms, right? 3 kilograms times 1 meter per second plus what? Plus 10 kilograms, that was given, times the final velocity, which we don't yet know, but we'll know it very soon, right? Because we've got 30 kilogram meters per second altogether. We subtract 3 from that, we get what? 27 kilogram meters per second divided by 10 kilograms is my final velocity, right? Which I believe will give me what? 2.7 meters per second. So is this an elastic collision? There's 2 ways to figure that out, right? The hard way is to calculate the kinetic energy. We could do that though, right? 1/2 mv, 1/2 times 3 times 100. So whatever that is, I think 150 joules to start with. And then afterwards, I've got, like 1.5 joules in M1 and I don't know, about, I'm not sure how many joules afterwards, but I already know it's not elastic though, right? Because if I look at it, the 1 velocity minus the 2 velocity is 10 meters per second, right? Afterwards, the 1 velocity minus the 2 velocity is 1 minus 2.7, which is minus 1.7. Minus 1.7 minus is not 10. So by the relative velocity theorem, this is not an elastic collision. It's an inelastic. So because V1 initial minus V2 initial is 10 meters per second, which is not equal to minus V1 final minus V2 final, which by the way is 1.7 meters per second. All right, that's my logic. So sometimes I ask though, I'm also interested in students being able to calculate kinetic energy. So like a lot of times on the test, I might also ask for what's the kinetic energy before, what's the kinetic energy after, and then comment, is this an elastic or an inelastic collision, all right? So this theorem though gives us a double check on that, right? All right. Let us look at another example here. All right, so this one, I have 2 students sitting on an ice pond in lawn chairs. One of them has an umbrella and a strong wind sends students A in collision course with student B. Suppose I give you the mass of the one is 60 kilograms and has initial speed of 2 meters per second in the eastern direction, whereas the 30 kilogram student has initially at rest. And after the collision, the one has a 1 meter per second speed at a standard angle 30 degrees. What's the final velocity of MB? I'll draw a picture here. So this is my example 5. So before, so this is before the collision, we have VA1 directly horizontal, and then like here's B, here's A. Afterwards, we have A is up here, and that's 30 degrees. And I put this angle down here, calling it beta. And here's B. And we'll call this VB2. And this is VA2. VA1 is given to be 2 meters per second. MA, I told you guys, is 60 kilograms, and MB is 30 kilograms. All right. So there's 2 questions here. It's find the final speed, or you find the final velocity, and then find the angle, this angle beta at which the mass goes there. All right. How should we solve this? Conservation of momentum. That's right. We cannot conserve kinetic energy because it wasn't given that this is an elastic collision, and generally speaking, it's probably not going to be. Okay, so here we go. We have, if you don't mind, I'm going to call this 2m. I'm going to call this m to avoid writing kilograms all over the place. So what we got here is 2m, right, times 2 meters per second, 0, right, is equal to m VA2. And then we've got ourselves a cosine of 30 degrees and a sine of 30 degrees. That's the direction vector of VA2. And we also have 2m, because that's the, oh, wait a minute, which one was 2m? My bad. This is supposed to be the 2, right? The 2 goes here, because A has twice the mass of B. So just one m over here. And, okay, VB2, which we don't know. And what do I got? I've got a cosine beta. But notice that it's downward, so I have to do minus the sine of beta. Right? And this gives us 2 equations and 2 unknowns, right? So like from the x component, we get what? We get like, first of all, you can divide by m. Divide by m, get rid of the m. So we get 4 meters per second is equal to 2 VA2 cosine 30 plus VB2 cosine beta. And from the y equation, we got ourselves 0 is equal to 2 VA2 sine 30 plus, or rather minus, VB2 sine the beta. Was I given VA2? In the problem statement, yes, I was. After the collision, A has a speed of 1 meter per second. If we didn't know that, we couldn't solve this problem, right? Because we'd have 2 equations and 3 unknowns if that was the case. But that's not the case. We're given that this is equal to 1 meter per second, all right? I just failed to write it down in my initial work here. So what's this tell me then? So what sine 30 is a half, right? So this second equation just becomes VA2 is equal to VB2 sine beta, yeah? In other words, this is equal to 1 meters per second. So I've got that. So I've got this on the one hand, cleaning up the equation above. I also have 4 meters per second. Well, let's say 4 minus the square root of 3 meters per second is equal to VB2 cosine beta. Right? So let me call this 1. You call that 2. I think dividing equations is a good move here again. If I divide equation 1 by equation 2, I get tangent beta is equal to 1 meters per second divided by 4 minus root 3. If you're wondering where the root 3 came from, guys, it's because the cosine of 30 is root 3 over 2. When I multiply by the 2, the half cancels, leaves me with root 3. I subtracted it to the other side. You could use decimals if you wanted to. Anyway, I sense a certain restlessness, which means I'm over time. And let me get to the point here. That works out to beta is 66 point, 2, phew, that was close, 21 degrees. And then if you plug that back into the other equation, you can get VB. This is problem 6.3.7 in my notes, and I'll stop there because we are out of time. But algebra aside, the larger point is set up momentum conservation, and we must think of momentum as a vector. All right, it is a vector, must think of it as such.